Welcome to today's session. We're diving into problem number 650, titled 2 Keys Keyboard. This problem challenges us to use a combination of copy all and paste operations to achieve an efficient solution. Let's explore the problem, approaches, and key takeaways. In this problem, you are working with a text editor that has very limited functionality. You can only use two operations, copy all and paste. Initially, the text editor starts with just one character, the letter A. Your task is to determine the minimum number of operations required to generate exactly n characters of it in the editor. Let's break down how these operations work. The copy all operation copies all the characters currently in the editor and saves them to the clipboard, replacing any previously copied content. The paste operation pastes the clipboard's content into the editor, adding the same number of characters that were copied. The input to the problem is a single integer n, which represents the target number of A's you need to create. The output will be the minimum number of operations required to achieve exactly n characters. Let's explore some examples to understand the problem better. Take the first example where n equals 3. We start with one A already in the editor. The first operation is copy all, which copies the single A to the clipboard. The second operation is paste, which adds the clipboard's content to the editor, resulting in 2 A's. Finally, a third operation paste adds another A, making the total 3. In this case, it takes exactly 3 operations to generate 3 A's. This sequence illustrates how we use the copy all and paste operations strategically to reach the target number of characters. Now let's consider another example where n equals 6. Again, we start with one A. The first operation is copy all, copying the single A to the clipboard. The second operation is paste, which brings the total to 2 A's. At this point, we use another copy all, updating the clipboard to contain 2 A's. Next, we perform a paste, adding 2 more A's and reaching 4 in total. Finally, one more paste adds 2 additional A's, bringing the total to 6. This sequence takes 5 operations in total. Notice how we used a second copy all operation when the editor contained 2 A's to minimize the number of steps needed. In the third example, we look at the case where n equals 1. Here, the text editor already starts with one A, and since the target is also 1, no operations are needed. The output for this case is 0. This demonstrates that when the initial state matches the target, no further actions are required. It's a simple edge case but important to consider when solving the problem. Finally, let's go over the constraints and some additional considerations. The value of n will always fall between 1 and 10,000. For the solution to be efficient, it must handle all valid values of n within this range. Edge cases to keep in mind include scenarios where n equals 1, where no operations are necessary, and when n is a prime number, as it requires a series of copy all and paste steps equal to the number itself. For larger values of n, the solution must remain computationally efficient. A key insight for solving this problem is that the minimum number of operations corresponds to the sum of the prime factors of n, where each prime factor represents a copy all followed by the necessary paste operations. This can be approached using dynamic programming or by leveraging the prime factorization of n to derive the result mathematically. The first approach we considered is the brute force method. Here, we attempt to explore every possible sequence of copy all and paste operations to determine the minimum number of steps required to generate exactly n A's. This involves using recursion to simulate all possible operations at each step and backtracking whenever the current sequence either exceeds n or becomes inefficient. The intuition behind this method is simple: by trying every possible combination, we can ensure that we find the optimal solution. For small values of n, this approach works well, as it guarantees we don't miss any possibilities. However, as n grows larger, the number of recursive calls increases exponentially, making this approach computationally impractical. The time complexity here is approximately 2 to the power of n, which quickly becomes infeasible for larger values of n. To address this, we turn to more efficient strategies, such as dynamic programming. Now, dynamic programming offers a more optimized solution by breaking the problem into smaller subproblems. We define dp, I, as the minimum number of operations needed to generate exactly I A's. To compute dp, I, we consider the factors of I. For example, if I equals 6, its factors are 1, 2, 3, and 6. The most efficient way to achieve I is to first generate one of its factors, j, and then paste enough times to reach I. This leads to the formula dp I equals min dp j plus I slash j, where j is a factor of I. Factoring I is crucial because the number of paste operations depends on how many times we can multiply an existing sequence of a's. Copying always costs one operation, while the number of pastes depends on the factorization. This approach ensures that we minimize redundant operations. With a time complexity of n squared, as we iterate through all numbers up to n and their factors, this method strikes a good balance between efficiency and accuracy. Additionally, we also considered a greedy approach based on prime factorization. Here, n is broken into its prime factors, and each factor contributes to the total number of operations. For instance, a prime factor p requires one copy all operation and p1 paste operations. The total steps are the sum of all prime factors of n. This method is highly efficient, with a time complexity of sqrt n, as we only need to check up to the square root of n to find its prime factors. However, it's less intuitive and harder to generalize compared to dynamic programming. Given the options, we chose dynamic programming as our primary strategy. While the greedy approach based on prime factorization is the fastest, dynamic programming offers a more general and systematic framework. It explicitly calculates the minimum steps for all intermediate values, ensuring correctness and making it easier to adapt to variations of the problem. This versatility makes it particularly valuable when the problem constraints or requirements change. In terms of trade-offs, brute force guarantees correctness but is impractical for large n due to its exponential time complexity. The greedy approach, on the other hand, is highly efficient with sqrt n complexity but relies heavily on mathematical properties, which can make it less intuitive and harder to extend. Dynamic programming balances these considerations, providing both computational efficiency and a clear, rigorous approach to solving the problem. With its reasonable n squared complexity, it serves as a robust middle ground, ensuring accuracy while offering deeper insights into the problem structure. The problem is about figuring out the minimum number of steps required to generate exactly n a's on a notepad using two operations, copy all and paste. The challenge is to sequence these operations optimally to minimize the total steps. To solve this, we use dynamic programming. The first step is understanding how the problem relates to breaking down n into smaller pieces. By decomposing n into its prime factors, we can split the task into manageable chunks, where each factor represents a group of repeated paste operations. Next, we define the state for our dynamic programming solution. Let dp I represent the minimum number of steps needed to generate exactly IAs. The base case is straightforward, dp 1 equals 0 since no operations are needed to get 1a, it's the starting point. From here, we build the solution iteratively for larger values of n. To compute the values of dp I, we use a transition state. For each number I from 2 to n, we identify all its divisors, j, up to the square root of I. If j is a divisor, then I can be expressed as j asterisk k, where k represents the number of repeated paste operations after copying JAs. Using this relationship, we calculate the minimum steps to reach I as dp I equals dp j plus k. This approach ensures that we account for all possible ways to construct I while minimizing the steps. After defining the transition, we compute the values of dp iteratively for all numbers from 2 to n using this formula. The result, dp n, gives us the answer. The key idea here is that the problem reduces to breaking n into its prime factors because each factor corresponds to a sequence of operations involving one copy all followed by multiple paste actions. By storing intermediate results in the dp array, we avoid redundant computations and achieve a significant efficiency boost. To further optimize the solution, we only iterate up to the square root of I when finding divisors. This reduces the computational complexity significantly, as we don't need to check all numbers from 1 to I. The main data structure used is a one-dimensional array called the dp table. This array has a size of n plus 1, where each entry dp I stores the minimum number of steps required to generate IAs. This structure allows constant time access for transitions and ensures efficient computation. In terms of complexity analysis, the time complexity is approximately O(n asterisk sqrt n). This comes from examining each number I from 2 to n and iterating through its divisors. The space complexity is O(n), which is used for storing the DP array. This combination of time and space efficiency makes the approach suitable even for large input values. The pseudocode illustrates how the algorithm is implemented. We initialize the DP array with zeros, then iterate from 2 to n, computing the minimum steps for each I by checking its divisors. The pseudocode continues with the computation of DP I. For each divisor j of I, we update DP I using the formula DP I equals min DP I DP j plus I // j, and also consider the symmetric divisor DP I equals min DP I DP I // j plus j. This ensures that both factors of I, j and I // j are accounted for in the dynamic programming transitions. The final result, DP n, is returned as the minimum number of steps required. Let's walk through an example to illustrate the process. For n equals 6, we initialize the DP array as 0, 0, 2, 3, 4, 5, 6, where each index represents the maximum steps needed if we simply used paste operations. To compute DP2, we find its divisor, 1, and calculate DP2 equals DP1 plus 2 is equal to 2. Similarly, for DP3, the divisor is 1, so DP3 equals DP1 plus 3 is equal to 3. These calculations show how the algorithm systematically builds the solution for each number up to n. Now, let's compute DP4 and DP6 to complete the example. For DP4, the divisors are 1 and 2. Using these, we calculate DP4 equals min DP1 plus 4, DP2 plus 2 equals 4. This means the optimal way to generate 4 A's is to copy all after reaching 2 A's, followed by 2 paste operations. For DP6, the divisors are 1, 2, and 3. The computations give DP6 equals min DP1 plus 6, DP2 plus 3, DP3 plus 2 equals 5. This shows that the optimal way to reach 6 A's is to first copy all at 2 A's and paste 3 times. The output for n equals 6 is therefore 5. Finally, let's consider edge cases. For n equals 1, no operations are needed, so the output is 0. For prime numbers, the number of steps equals n because we must copy all once and paste n 1 times. For large numbers, the algorithm remains efficient due to the divisor-based optimization, ensuring it scales well even for high values of n. This implementation solves LeetCode problem number 650, 2 keys keyboard using a dynamic programming approach. The task is to find the minimum number of steps required to generate exactly n A's using the operations copy all and paste. #explanation. 1. Base case, if n is 1, no steps are required because the initial notepad already has 1. Therefore, we return 0. 2. Dynamic programming table, we use a list DP where DP, I, represents the minimum number of steps required to generate IAs. The table is initialized with zeros, and its size is n plus 1 since we calculate up to n. 3. Iterating over numbers, starting from 2 to n, we calculate the minimum steps for creating each number of A's. Initially, we assume the worst case for DP, I, to be I, all steps are paced after a single copy all. For finding factors, for each I, we check all possible factors j, from 1 to I/2. If j is a factor of I % j equals 0, then we can generate I by first creating j A's and then performing I/j paste operations. The steps required are DP, j, plus I/j. We update DP, I, to be the minimum of its current value and this calculated value. 5. Result, finally, DP, n, contains the minimum number of steps to generate NAs, which we return. #complexity. Time complexity, the outer loop runs n times, and for each I, the inner loop checks up to I/2 factors. In the worst case, this results in a time complexity of approximately O(n sqrt n), because factorization is bounded by the square root of the number. Space complexity, the space required is O(n) for the DP table. This approach ensures an optimal solution, leveraging the dynamic programming paradigm to minimize redundant calculations and efficiently compute the result. This is the Java implementation of LeetCode problem number 650, 2 keys keyboard. The solution uses a dynamic programming approach where we calculate the minimum steps required to produce NAs. The logic mirrors the Python implementation, with adjustments for Java-specific syntax, such as array declarations and the use of math.min for comparisons. The DP array stores the minimum steps for each number of A's, and we iterate through possible factors of I to minimize the steps. The base case handles n equals 1 directly. In this problem, we need to figure out the minimum number of operations required to print exactly NAs on a notepad. We start with one already on the notepad and have two operations available: copy all, which copies all the text currently on the notepad, and paste, which pastes the last copied text. The challenge is to determine the most efficient sequence of these operations to achieve exactly NAs. To solve this, we use dynamic programming. The idea is to create a DP array where DP, I, represents the minimum steps required to achieve exactly IAs. To illustrate, let's walk through the example where n equals 3. First, we initialize the DP array as 0, 0, 0, 0. For the base case, DP 1 equals 0 because no operations are needed when we already have one. Next, for I equals 2, we initially assume the worst case where it takes two steps, one copy all and one paste, so DP 2 equals 2. Then, we check the factors of 2. Since 2 is divisible by 1, we can achieve 2 A's by copying the 1 and pasting it twice. This gives us DP 2 equals DP 1 plus 2 equals 2. Moving on to I equals 3, the worst case assumes 3 steps, 1 copy all and 2 paste operations, so DP 3 equals 3 4 now. To refine this calculation for I equals 3, we check its factors. Since 3 is divisible by 1, it's possible to achieve 3 A's by copying the single A and pasting it 3 times. This results in DP 3 equals DP 1 plus 3 equals 3. With that, we conclude that the minimum steps to achieve 3 A's is exactly 3. Next, let's look at the example where n equals 6. Here, we initialize the DP array as 0, 0, 0, 0, 0, 0, 0, and the base case remains DP 1 equals 0. For I equals 2, the worst case requires 2 steps, so DP 2 equals 2. Checking the factors of 2, we see that 2 is divisible by 1, allowing us to update DP 2 equals DP 1 plus 2 equals 2. Similarly, for I equals 3, the worst case is 3 steps, and checking its factors confirms that DP 3 equals DP 1 plus 3 equals 3. For I equals 4, the initial assumption is 4 steps, but we then check its factors. Since 4 is divisible by 1, we update DP 4 equals DP 1 plus 4 equals 4. Additionally, since 4 is also divisible by 2, we find a better solution: DP 4 equals DP 2 plus 2 equals 4. Finally, for I equals 6, we start with 6 steps and begin checking its factors. For I equals 6, we first note that 6 is divisible by 1, so we update DP 6 equals DP 1 plus 6 equals 6. Next, since 6 is also divisible by 2, we calculate DP 6 equals DP 2 plus 3 equals 5, which is an improvement. Finally, 6 is divisible by 3, and this allows us to update once more: DP 6 equals DP 3 plus 2 equals 5. This means the minimum steps required to achieve 6 A's is 5. Now, for the case where n equals 8, we initialize the DP array as 0, 0, 0, 0, 0, 0, 0, 0, 0, and follow the same process. After iterating through each number from I equals 2 to I equals 8 and checking all possible factors, we find that the optimal sequence for I equals 8 involves utilizing the factor 4. Specifically, we use the value at DP 4 and add 2 steps for a copy and paste, resulting in DP 8 equals 6. The key insight here is that the solution relies on finding the factors of I and using those to determine the optimal combination of copy all and paste operations. By iteratively updating the DP array, we ensure that we find the most efficient way to achieve exactly NAs. To analyze the time complexity of our dynamic programming solution, we start by looking at the 2 nested loops. The outer loop runs from I equals 2 to I equals n, meaning it executes in 1 iterations. Within this loop, we have an inner loop that iterates over all integers j from 1 to I //2. The purpose of this inner loop is to identify the factors or divisors of I. For each value of I, the inner loop performs up to I/2 iterations in the worst case. Additionally, within the inner loop, the condition if I%j == 0 is checked to determine if j divides I evenly, and this divisor check is an O(1) operation. By combining the work of the outer and inner loops, we can start to build an understanding of the total computational cost of the solution. The total time complexity is derived by summing the number of inner loop iterations across all executions of the outer loop. For example, when I = 2, the inner loop runs for 1 iteration. When I = 3, it also runs for 1 iteration. For I = 4, it runs for 2 iterations, and so on. By summing these iterations up to I = n, we observe that the total number of iterations is proportional to the sum of all divisors of integers from 2 to n. According to number theory, the sum of divisors for numbers up to n grows asymptotically as O, n * log n. Therefore, the overall time complexity of this algorithm is O, n * log n, **, as the dynamic programming approach focuses on factorization checks and avoids redundant computations. In terms of space complexity, the solution primarily relies on a dynamic programming table, dp, which has a size of n+1. This table is used to store the minimum steps required to generate IAs for each value of I from 1 to n. The memory required for this table is proportional to n, or O, n. Additionally, the algorithm uses a small number of auxiliary variables, such as I, j, and a few others, which require constant space. This auxiliary space adds an O(1) term to the space complexity. However, since the dp table dominates the space usage, the total space complexity of the solution is O, n. To highlight the efficiency of the dynamic programming solution, let's compare it to a brute force approach. A naive method would try all possible sequences of copy and paste operations to generate NAs. This approach has exponential time complexity because it explores every possible combination of operations, making it highly inefficient for large n. In contrast, the dynamic programming solution improves significantly upon the brute force method by leveraging memoization. Instead of exploring every sequence, it focuses only on valid factorization steps, reducing the time complexity to O, n * log n **. Moreover, the time complexity remains consistent across best, average, and worst cases because the algorithm always iterates over all numbers from 2 to n and checks their divisors. This consistency makes the solution both efficient and predictable. The O, n * log n ** time complexity of this algorithm can be further justified mathematically. The inner loop iterates over the divisors of I, and the total number of iterations is proportional to the sum of all divisors up to n. From number theory, we know that this sum grows asymptotically as O, n * log n **, which confirms the time complexity. Regarding space, the dynamic programming table of size n+1 dominates the space usage, leading to a space complexity of O, n. Together, these analyses confirm that the dynamic programming solution offers a highly efficient and scalable approach to solving the problem, both in terms of time and space. Understanding the common mistakes in solving this problem is crucial for building efficient solutions. First, misunderstanding the problem requirements can lead to errors, such as assuming you can paste without performing a copy all operation first. This violates the constraints and results in invalid or wasted operations. Next, overlooking edge cases is another frequent issue. Consider scenarios like n = 1, where no operations are needed, or smaller values of n that require very specific sequences to solve. Missing these can lead to incorrect outputs even for the simplest inputs. Another mistake is relying on brute force without optimization. While brute force might work for small n, its computational cost grows exponentially as n increases, causing timeouts on larger inputs. Lastly, ignoring factorization patterns is a major oversight. The key to minimizing operations lies in breaking n into its prime factors. Without this insight, solutions tend to be suboptimal and less scalable. Errors in calculating the number of steps are also common. For instance, forgetting the initial copy all step or miscounting repeated paste operations can lead to off-by-one errors and ultimately incorrect results. A critical insight for solving this problem efficiently is recognizing that the goal is to minimize the number of operations by strategically using the copy all and paste commands. This boils down to factorizing n and translating those factors into operations. For example, if n is 9, its prime factorization is 3 times 3. This means you would perform one copy all operation, followed by 2 sets of 3 paste operations. To optimize further, always aim to break n into its smallest prime factors, as each factor directly contributes to the total number of steps. While brute force approaches are simple, they are computationally expensive. On the other hand, leveraging prime factorization significantly reduces time complexity, though it requires a deeper understanding of the underlying math. This problem connects to several related topics in LeetCode. The most directly related is LeetCode 650 itself, the 2 keys keyboard problem. Other problems, like LeetCode 263, ugly number, also involve factorization concepts, specifically breaking numbers into prime factors. Similarly, LeetCode 264, ugly number 2, focuses on generating numbers with specific factors using dynamic programming. Another relevant problem is LeetCode 517, super washing machines, which involves minimizing operations, a theme shared with this problem. There are also alternative approaches to solving the 2 keys keyboard problem. A dynamic programming method involves creating a DP array where each element represents the minimum steps needed to reach that number of A's. This approach is intuitive but has a time complexity of n squared. Alternatively, a greedy approach uses factorization, summing the prime factors of n to calculate the steps. This method is faster, with a complexity of n, but requires an understanding of prime factorization. Finally, iterative simulation can be used for small values of n by exploring possible sequences of operations. While simple, this method is inefficient for larger inputs due to its exhaustive nature. Great job! To wrap up, we reviewed problem number 650, tackled its complexities, and highlighted the importance of mathematical insight. Remember, practice makes perfect. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!